In this video, we want to compare OSPF with EIGRP. Both are enterprise class routing protocols, but here in the Encore course, Cisco doesn't really have anything else about EIGRP. We just need to know primarily about OSPF, except there is an item on the blueprint where we need to compare the characteristics of OSPF with EIGRP. You'll get more into EIGRP if you take the NARCE exam and study for that. That's one of the concentration exams as part of the CCNP Enterprise Cert Track. But here, we just want to do a high-level comparison between OSPF and EIGRP, and we're going to compare based on the following criteria. We're going to compare the category of routing protocol that each protocol falls into. We'll compare their administrative distance, see which one is more believable than the other. We'll talk about how each calculates their metric. Timers work different. We'll distinguish between OSPF and EIGRP timers. And finally, we'll talk about how they differ in terms of load balancing. But let's begin by understanding different categories of routing protocols and seeing where OSPF and EIGRP fit in. First, let's consider these three different categories: distance vector, link state, and path vector. Distance vector tells us in which direction do we go to get to a destination network and how far is it. If you think about your high school physics class, or maybe in college and you learned about a vector, remember a vector gives us two pieces of information. It gives us magnitude and direction. In other words, go this way and here's how far it is. That's what a distance vector routing protocol does. It doesn't know the entire path that we have to go. It just knows the next hop is in this direction. We're going to go to this next hop IP address, or we're going to go out of this egress interface, and here's a metric or a cost representing how far it is to get to that destination network. And a link state routing protocol is going to have a map of the entire topology. The link state routing protocols use an algorithm. It's called the Dijkstra algorithm. It's the same algorithm that works on our navigation systems in our cars, or if you have Google Maps on your smartphone. Those navigation systems that give you directions, they have a map of the entire topology that you're going to be traversing, and they are going to assign a cost to each path. And it's going to mathematically determine the lowest sequence of next hops that will get you there with the least cost. So link state routing protocols don't just say go in this direction and here's how far it is. It can look at the entire map of the topology, and all the routers within this area of the topology, they've got the same map, so they all agree on how to get from point A to point B. And a path vector, and we're going to see that only applies to BGP, a path vector is going to say, yes, here's the direction that you go, and no, we don't have a map of the entire topology, but we do know the path. We know the autonomous systems that we have to transit to get to the destination network. Now let's put these different protocols into categories. RIP, the Routing Information Protocol, that's a distance vector routing protocol. It says go out of this egress interface or go to this next hop IP address, and here's how far it is. Here's the hop count. RIP measures how many routers we have to traverse or hop through in order to get to the destination network. And by the way, 15 is the maximum with RIP. If something is 16 router hops away, it's considered to be unreachable. Now, OSPF, the main focus of this Encore course, is a link state routing protocol. It's got a map of the entire topology. And ISIS, intermediate system to intermediate system, that's also considered to be a link state routing protocol. And it also uses that Dijkstra algorithm. Now, EIGRP, that's what we're comparing OSPF with here in this video. EIGRP, the Enhanced Interior Gateway Routing Protocol, it does fall under the distance vector category, but it's an advanced distance vector routing protocol. And what I mean by advanced is it's not as fundamental as RIP, just saying, here's the best path, and here's how far it is, and here's where I'm going to go next. No, EIGRP can pre-qualify one or more alternate routes. Yes, it'll find the best route, and we'll talk a little bit about how it does that in this video. But if that best route were to fail, we don't have to go through a big, massive calculation in all cases to see, all right, is there another way to get there? No, it's almost like we have a hot standby route standing by that we can switch over to in a matter of just like a couple of seconds or so. So it's an advanced distance vector routing protocol. And BGP, the Border Gateway Protocol, that's often thought of as the routing protocol of the internet. As different autonomous systems are interconnecting, they're going to typically speak BGP between themselves. And BGP keeps track of the autonomous systems we have to transit to get to a destination network. But with OSPF, the main protocol we're focusing on in this course, I said it's going to have a map of the topology. I want you to think of that map much like a puzzle. And that map is stored in something called the link state database. Now, this is a puzzle one of my daughters was working recently, and it had like 1,500 pieces to it. And as I saw it, it reminded me a lot of OSPF. And I said, I've got to take a picture of this to show my OSPF students. The reason I say it reminds me of OSPF is she was working on this with her boyfriend at the time, fiance now, and they would help each other, and they would say, do you have Cinderella's slipper or whatever it was? And they would share pieces back and forth, and slowly, over many days, they put together this puzzle. Well, it's the same thing with OSPF, with Open Shortest Path First. We've got different routers that know about different parts of our topology, different parts of the network. They're connected to different parts of the network, and they're going to share information. This information is contained in LSAs, link state advertisements. And these link state advertisements are essentially like these puzzle pieces. We share the LSAs between all of our members, and together, our collective IQ, if you will, amongst all the routers in the network, they can assemble this map of the topology, much like different people can assemble a puzzle because they each have pieces of the puzzle. When you put them all together, everybody has the same view of the puzzle, just like all the routers within an OSPF network. They've got the same view of the network once everybody has the same complete link state database. Another comparison between EIGRP and OSPF is administrative distance. Administrative distance is the believability of a routing source. For example, here R5 is being told by various sources how to get to network 10.1.1.0/24. R1 says, this is the way to that network. R2 says, here's how to reach that network. R3 says, I'll get you there. And R4 says, here's your ticket to 10.1.1.0/24. Who do we believe? Well, it depends on the source of the routing information, and each type of route information source has an associated administrative distance value, and the lower the value, the more believable that source. If we have a network that's directly connected to us, well, that's pretty believable. We know that that network is connected to us. We know how to get to that network because we're part of that network. And that's the most believable of all. So that has an administrative distance of a 0. However, we could have a static route that we administratively add to the router. By default, it's going to have an administrative distance of a 1. So that's pretty believable. But then we start to get into our dynamic routing protocols. EIGRP has an administrative distance of a 90, and OSPF has an administrative distance of 110. That means that EIGRP is going to be more believable than OSPF. Now, by the way, this is for EIGRP within a network. In other words, it's within an autonomous system. We're not redistributing another autonomous system into EIGRP. If something gets redistributed into EIGRP, that EIGRP route is going to have an administrative distance of 170. But here, we're assuming that everybody's part of the same network, and we've got an administrative distance of a 90. Now, RIP is less believable still with an AD of 120. So that's another comparison between OSPF and EIGRP specifically. EIGRP is a little bit more believable. Now let's consider how OSPF and EIGRP are going to calculate the best path to get to a destination network. OSPF is going to use a metric of cost, and the lowest cost path is going to win. And the cost is the reference bandwidth divided by the interface bandwidth. And by default, and we can change this, but by default, the reference bandwidth is 100 megabits per second. And we're trying to get from PC1 to PC2 on screen. And one way, we could go from R1 to R2 to R3 and then out to PC2, or we could go from R1 to R3 and then out to PC2. If we were running a routing protocol like RIP, which only takes into account hop count, it doesn't pay any attention at all to bandwidth, then it would say, oh, it's a shorter hop count to go from R1 to R3 out to PC2, as compared to going from R1 to R2 to R3 out to PC2. It's one fewer hop. But we can look at this and say, I don't want to use that path of R1 to R3 because that's a 10 meg link. I'd rather stay on the 100 meg links. And OSPF is going to agree with us. So let's see how OSPF would calculate this cost. OSPF would say the reference bandwidth is 100 meg, the link speed is 100 meg, and 100 divided by 100 is 1, so we can give a cost of 1 to each of our 100 meg links. What about that bottom link from R1 to R3? Well, that's the reference bandwidth of 100 divided by the link speed of 10. That's going to be a cost of 10. So we can tell from this that we would rather go from R1 to R2 to R3. That's going to be a total cost of 3 as compared to going from R1 to R3 and then out to PC2, which would have a cost of 11. So here is our preferred path. Here's a word of caution though. Notice I said that the default reference bandwidth was 100 megabits per second. What if we had a gig link, which is very common, or a 10 gig link? If we had a gig link and we had 100 meg divided by 1000 meg, a gig, what would the cost be? Well, it would seem to be a decimal of 0.1. We're not allowed to have decimal values for our cost. So what would we do? We would round up to a 1. If we had a 10 gig link or a 100 gig link, they would all be a decimal value and they would all round up to 1. That means by default, from OSPF's perspective, we've got the same cost for a 100 meg link as we do for a gig, a 10 gig, or even a 100 gig link. That's not good. What can we do? Well, as a best practice, I like to set my reference bandwidth to a higher value. I like to set my reference bandwidth to something like 200 gigabits per second. That way, those different high bandwidth links, they're going to have different cost values. So just a real world caution for you. Now let's compare this cost calculation and path selection with EIGRP. EIGRP considers more than just bandwidth, and here's an acrostic to help you remember this. Remember the acrostic, big dogs really like me. Big dogs really like me. And the B in big is going to remind us of the B in bandwidth. That's one of the things that EIGRP can consider. The D in dogs reminds us of the D in delay. The R in really reminds us of the R in reliability. The L in like reminds us of the L in load. And the M in me reminds us of the M in MTU. Now let's talk about each one of these. The bandwidth is really the weakest link. As we're going through all these routers to get to our destination, whichever link is the slowest bandwidth, that's the value that we're going to be using for the bandwidth. In fact, the way we calculate bandwidth is we take 10 to the 7th power and we divide it by the link speed. That's the slowest link from point A to point B. The delay is cumulative. It's not the weakest link. Every time we exit a router interface, we're adding on a little bit of delay. So delay is cumulative. And we'll get more into this in the NARCI course if you join us for that one. Reliability, though, it talks about how reliable the link is. And it's some number over 255. If we're not dropping packets, we're 100% reliable, then that value is going to be 255. The load describes how busy our link is. Even though a link might be a high-speed link, if it's congested, it's still not a good link for us. So load is a number over 255, where a minimally loaded link would have a value of a 1 over 255. So we might have a load of 1. That would be a minimally loaded link. And as a tiebreaker, we could use an MTU, the maximum transmission unit. The default is 1500 bytes for a packet, but sometimes we reduce the MTU because we have some extra header associated with a tunnel or different reasons. But the highest MTU can win as a tiebreaker. The MTU itself, though, does not go into the formula. And the formula is a bit intimidating, to be honest. Here it is. Here's the formula for the EIGRP metric. Now, I don't expect you to memorize this for the exam, but I want you to understand that there are ways of influencing the metric to pay more attention to bandwidth or delay or reliability or something like that. For example, if I wanted to pay more attention to the bandwidth value, I could change that K1 variable to a higher number. By default, that K1 value is a 1. In fact, here are all of the default K values that we have with EIGRP. Now, this is with traditional EIGRP. There's something now called named EIGRP, where we actually have a 6th K value. Again, we'll get into that in the NARCI course. This Encore course isn't focused on EIGRP, but notice the default K values. There are 3 of them that are zeros. K2, K4, K5, they're all zeros. And if we plug all those in, the formula honestly kind of breaks down. Look at that K5. You see the K5 is 0, and part of the formula is K5 divided by K4 plus the reliability. Well, if K5 is 0, that whole thing is 0, and we're multiplying 0 times everything in the parentheses, it's all going to be 0. Well, there's an exception to this. It says that, yeah, this is the formula unless K5 is 0. If K5 is 0, then we assume that K5 over K4 plus reliability, we assume that entity is a 1. I know it kind of breaks the rule, but that's the way it works. Now, if you do the plugging and chugging, you'll see that it really falls out to where EIGRP is really only considering bandwidth and delay by default. In fact, that was a question I missed on a technical interview. When I was getting a job down at Walt Disney World as a network designer, they used EIGRP on over 500 routers at Disney World, and they asked me, by default, what does EIGRP use to determine the metric? And I knew this acrostic, so I rattled it off. I thought, big dogs really like me. And I said really quickly, I said, it's bandwidth, delay, reliability, load, and MTU. And they said, no, that's wrong. And I thought, what do you mean it's wrong? But then they pointed out that they had asked by default. By default, we've got all these 0K values. We're not using MTU as a tiebreaker. By default, we're only considering bandwidth and delay. And that's how the metric is calculated. Now let's see how EIGRP will use that metric in making its path selection decision. Take R3 for example. Let's say that R3 wants to get to the network of 10.1.1.0/24 on the left-hand side of your screen. It can get there from R1 or R2. It's got two EIGRP neighbors, and they're each going to report their distance from the network, their metric. Now, each of those routers, R1 and R2, their metric to get to 10.1.1.0, they're directly attached. Their metric is, we'll say 1,000. Okay, they're going to report that information to R3. R1 says, I can get there in 1,000. And R2 says, I can get there in 1,000. But R3 realizes that it's going to cost something to get to R1. It's going to cost something to get to R2. So R3 is going to say, let me add those up. R1 reported a metric of 1,000 to get to that network. That was the reported distance. You see there on the column of RD, reported distance, R1 reported that to me of 1,000. But it cost me 10,000 because maybe I'm on a serial link. Maybe it's a 10,000 cost for me to get to R1. Well, I've got to add those two up. 10,000 plus 1,000, that's 11,000. That gives us what's called our feasible distance, or the FD. What if I went via R2? Well, it reported 1,000 metric to me as well. How much does it cost me to get to R2? 5,000. Let's add those up. 1,000 plus 5,000 gives us a feasible distance of 6,000. And I'm going to go with the lowest feasible distance. And that's going to be the path via R2. That's how EIGRP calculates its metric and makes a path selection decision. Another distinction I want to make between OSPF and EIGRP in this video deals with timers. When we talk about timers, we're talking about a conversation that goes on between neighbors, be they OSPF neighbors or EIGRP neighbors. In order for one router to know that its neighbor is still there, it expects to hear a hello message from that neighbor periodically. And the timers work a little bit different with OSPF and EIGRP. With OSPF, we have something called a hello interval. And there are default values for the hello depending on what kind of network we're on, and we can certainly set that. But I want you to know about the hello interval. That says how long we as a router are going to wait before we send another hello message to our neighbor. So we have a hello interval, and we've also got a dead interval. That says, how long am I going to wait to hear a hello from my neighbor before I consider that neighbor to be no longer available? And OSPF neighbors, they have to have matching timers. They have to agree on how often are we going to be sending these hellos to one another, and how long are we going to wait before I consider you to be down. Compare that with EIGRP. EIGRP has the same kind of hello interval. It says how long are we as a router going to wait between sending our hello messages to our neighbor. But here's where it gets different. EIGRP does not have a dead interval. It has something called a hold time. And this says not how long we are going to wait to receive a hello from our neighbor. This is information that we send to our neighbor. We're telling our neighbor, wait for me for this long. If you don't hear from me for this duration of time, consider me to be down. So again, the big difference is OSPF has the dead interval, and it says, if I don't hear from my neighbor within this time, they're dead to me. But with EIGRP, I'm telling my neighbor, hey, wait for me for this long, then you consider me to be down. It's like when I'm going into a cave and I say, if you haven't heard from me in 20 minutes, send help or something. We're telling our neighbor how long to wait for us with EIGRP. That's the difference. And finally, let's compare how load balancing works between OSPF and EIGRP. With OSPF, we can load balance across equal cost paths. Now in this example, with this topology on screen, let's say that we're sending traffic from a device off of SW1 to a device off of SW3. Well, as we go down the topology and we get to R2, R2's got a couple of ways of getting to SW3. It could go via R3 or it could go via R4. Now, OSPF is going to consider only bandwidth in its calculation, and notice the link speeds. They're different. We have a 256K link between R2 and R3. We've got a 512K link between R2 and R4. So OSPF is going to say, I'm going to choose the best link. I'm going to go from R2 to R4. Yeah, I might use R3 as a backup if R4 were to go down, but I'm going to just use R4. It kind of seems like we're wasting bandwidth, doesn't it? I mean, sure, it's not as fast, but I could still be sending some traffic via R3. I could send more via R4, but it'd be nice if I could send some via R3 as well. OSPF doesn't do that, but EIGRP can. EIGRP has a feature called the variance feature, and the variance feature is a multiplier. Let me show you what I mean. Let's say that the feasible distance from the perspective of R2 to get to this network off of SW3 is about 10.5 million. And if we go via R4, the cost is about 5.5 million. Well, what we can do in EIGRP router configuration mode is give the command variance followed by this multiplier. And let's say it's variance 2. If we multiply our best feasible distance, which is just over 5.5 million, if we multiply that by 2, the variance multiplier, we get about 11 million. What we're saying is now we will load balance across any link whose feasible distance is less than that 11.0289992 million. Not equal to, but less than that value. Now, think about that link via R3. It's about 10.5 million. Is it less than the 11 million number? It sure is. So even though it's not as good of a link as compared to the link going to R4, we can still use it. We can still load balance across it if we configure the variance feature. Now, by the way, if we do this, EIGRP is going to be really intelligent about this, and it's not going to try to send an equal amount of traffic via R4 and R3. It knows that R4 is better. It's going to give a proportionally higher amount of traffic to the link going to R4 as compared to the link going to R3. But this lets us use what would be just a dormant standby link with OSPF. It lets us actively use it to send traffic. And that's a comparison between some of the key features of OSPF and EIGRP.